Hi, my name is Mengmi. This is a joint work with Philip, Dimitar, Spandan, Claire, and Gabriel. The object in the sky cannot be pig. Context plays an important role in visual recognition. For example, this is supposed to be a huge chair in the parking lot. However, this inconsistent context tricks neural nets into mislabeling the target into something else. Together with other existing works studying context in recognition in our previous work, we have been focusing on modifying fundamental properties of context on natural images. However, similar as other cut-and-paste datasets, a drawback of these datasets is the introduction of artifacts such as unnatural lighting. While some out-of-context datasets consist of real images, these datasets are often limited in sizes and diversity. And most importantly, it is a daunting task to outsource such out-of-context natural images, especially when contextual rules are violated. Moreover, none of the datasets mentioned above allow systematic analysis of individual properties of context. To address these challenges, we introduced a large synthetic out-of-context dataset by leveraging a 3D simulation engine. The ability to rigorously control every aspect of the environment enables us to systematically violate contextual rules and assess their impact on recognition. The figure on the left shows an example where the gravity rule is violated. The target is a plate, as indicating the red bounding box. With the Unity 3D simulation engine, we can systematically control its gravity and lift the plate 8 inches above the table. In the experiments, we benchmark object recognition accuracy on humans using Amazon Mechanical Turk. We studied 6 fundamental contextual conditions, such as gravity, co-occurrences, and relative sizes. Here is the experimental schematic on MTurk. Subjects were first presented with a fixation cross for 500 milliseconds, followed by a bounding box indicating the target object location with another 1 second. In most experiments, the image under various contextual conditions was shown for 200 milliseconds. After image offset, subjects type one word to identify the target object. In parallel to human psychophysics experiments, we proposed a new context-aware architecture named the CRT-net, and we evaluate its performance on the same contextual conditions as humans. CRT-net is presented with an image with multiple objects and a bounding box to indicate the target object location. The model has 3 elements. First, CRT-net uses a stack of transformer decoding layers with multi-head attention to hierarchically reason about the context and integrate contextual cues with object information. Second, a confidence weighting mechanism improves the model's robustness and gives it the flexibility to select what information to rely on for recognition. Third, we curated the training methodology with gradient detachment to prioritize important model components and ensure efficient training of the entire architecture. Context modulation matters in object recognition. Due to time limit, I'm only going to present the results when gravity is violated. Since contextual modulation effect is more prominent on smaller target object sizes, we constrain the size of the target objects to be below 2 degrees visual angle. To study the effects of contextual areas, we introduce minimal context to full context conditions. Compared with the minimal context, full context largely improved the human recognition accuracy. From the bar plot, we see that the gravity condition was even slightly worse than no context condition. This implies that wrong context hurts object recognition. On the right of the bar plot, we are showing our model performance. This gravity effect was also readily captured by CRT-net. We also compare our model performance with other comparative methods. Our model achieves the highest linear correlation values among all the methods. To summarize, we introduced a large synthetic out-of-context dataset with fine-grained controls. We conducted psychophysics experiments to quantify human recognition accuracy. We also proposed a transformer-based model for recognition. It approximates human-level performance without retraining for each task. Please refer to our GitHub page for more information. Thank you.